All right, so chapter 6 is on chemical reactivity and mechanisms. And the first thing we need to review from Gen Chem is enthalpy. What is enthalpy? It's heat energy released from a reaction, right? So let's make a little review chart. Enthalpy is the measure of the amount of energy released or absorbed by a reaction. And it's important to remember, too, that this is under constant pressure. All right, let's think about this. What's the symbol we use for enthalpy? H. Okay, if delta H is negative, what does that mean? It's, what was it? I heard it in the back. Exothermic. So negative delta H means we're releasing heat from the reaction. So it's exothermic. If delta H is positive, what do we call that? Endothermic. So endothermic means that if you felt that reaction, it would actually feel cold because it's absorbing heat from you. So it has to do with the heat flow. Is the heat flowing out of the system or into the system? And we can measure delta H values pretty easily, assuming you have a chart. So delta H can be measured using bond dissociation energies. And the table in your book that shows a lot of these is table 6.1. This is a really nice table that you can refer to. So if you do have your book with you, you can even crack it open, but I'll leave this on the screen. But it's important to make a list. Make a list of bonds broken and bonds made. And this will make more sense with an example reaction. So let's choose an example. In this example reaction, I've got this 3-carbon chain. What would we call this? Propane. Say it with a Texas accent if you want. Nobody laughed. That's terrible. All right. We can react this with bromine, and we're going to learn about this reaction mechanism a little later, but we can react bromine, Br2, with propane under UV light. What you end up forming is 2-bromobutane and HBr. So let's do this. We've got bonds made, or actually, sorry, let's do bonds broken on this side. And then bonds made. HV, that's chemical speak for UV light.
Wait. Yeah. Why?
I didn't make the rules. Yeah, UV light's just written with HV, so it's Planck's constant times frequency. It's the symbol for UV light. Yeah. All right, so let's look at bonds broken. What bonds did we break from our starting materials? Okay, so we broke Br-Br. What other bonds did we break? Carbon-hydrogen, right? Specifically, we've got a hydrogen that was coming off of the central carbon. Right? So I could show it as that bond, indicating that it's coming off of the middle carbon, not one of the terminal carbons. So we broke 2 bonds. And then if we think about the bonds that were made, what bonds did we make? Yeah, hydrogen and bromine. That's a new bond. And then what else? Yeah, so we've got a bromine, CH, CH3, 2. All right, so now let's go up, and we need to look up the energies. All right, so for bromine, go to our chart. You can see bromine here. And I like using kcals per mole. You can use kilojoules per mole. It really doesn't matter. Both are used interchangeably. The SI unit is kilojoules per mole, but a lot of American chemists use kcals per mole. So let's just use kcals per mole because it's a smaller number. All right, so that's 46 kcals per mole. So 46 kcals per mole. And do you think the sign should be positive or negative if we're breaking this bond? Does it take energy to break it? Yes. Yes, it takes energy to break a bond, which means it's going to be positive. So anytime we look up a bond dissociation energy, if you're breaking it, it's positive. If you're making it, it's negative. All right, now let's go up and look at the second bond we made, second bond we broke. If we go in our chart, it's located right here. So it takes 95 kcals per mole to break that bond. So we'll tag this in here. Okay, and then we'll go to bonds made. We need to look for a HBr bond that was made. So let's go back to our chart. Or is it HBr right here? It's 88 kcals per mole. So let's slide down. Got 88 kcals per mole. And is that going to be positive or negative now? Negative. So negative 88. And then Br got added into that central carbon, so we'll go over here. And it looks like that is 65 kcals per mole. Right? Is that the right one? No. Wrong one. Up here. 68 kcals per mole. Okay, so this is negative 68 kcals per mole. Now we need to look at our list and we need to determine whether or not this reaction is exothermic or endothermic. How do we do that? Add them all together. So if we sum all of this together, we have 46 plus 95 minus 88, whoops, minus 68.
It's going to be exothermic.
Okay, why?
Because it's going to be negative 15.
Okay, perfect. So we've got negative 15 kcals. I wasn't sure if that was a question or not. Kcals per mole. The reaction is exothermic, meaning it releases heat. There we go. So you can use these tables of bond dissociation energies to predict whether or not a reaction is going to be exothermic or endothermic. One thing I will say is that this table is pretty small. It's not an exhaustive list. So sometimes you have to find the closest match that you can. You may be off by a kcal or two, but that's fine. Doesn't matter. Just make a good, educated guess. If you go to some Gen Chem textbooks, they even have appendices full of tables of bond dissociation energies. But with OChem, this is plenty good enough. Yep. Yep, bonds that are made are always negative. Bonds that are broken are always positive. Yep.
Isn't entropy calculated by the products minus reaction?
There are some instructors that do it that way, but I prefer to just do the positive and negative and then sum everything together. It avoids flip-flopping things. Yep, so let's even add that in. So bonds broken are always going to be positive. Bonds made are always going to be negative. All right. The other important thing to remember is that enthalpy isn't the whole story, right? We've got entropy going on. So let's make a little note. Delta H on its own is not a good measure of a reaction's spontaneity. We must consider entropy as well. What is entropy? Disorder or chaos, right? So entropy is the other half of the reaction, right? Not only do we have to worry about whether or not it's releasing or absorbing heat, but we have to worry about how ordered or disordered the system is becoming. So let's switch gears and talk about entropy and briefly review the concepts behind that. Entropy is a measure of disorder. So the example I like to do, but I forgot to bring it in today, is if I had a bottle of perfume and I spray it up here, what happens to the perfume? It disperses through the room. It's the natural order of the universe for things to become more disordered. It actually brings a lot of interesting philosophical questions. Do any of you guys play Cards Against Humanity? Yes. Yeah. So one of the cards I got said the inevitable heat death of the universe. And I started laughing really hard because it was a reference to entropy, right? Eventually our universe will expand and be so disordered that things will be so cold that our universe will die. Nobody else in the group thought it was funny, but I thought it was close. All right. That was the only chemist. So let's think about that. If we've got delta S of our system is positive, if delta S is positive, does that mean we have more disorder or less disorder? Actually, more. So in this case, delta S, if it's positive, is more disorder. And if delta S of our system is negative, then it's less disordered. Why did I put delta S of our system? Yeah, because if we're considering S total, meaning the overall universe, that's a completely different story than the reaction in and of itself. So as chemists, we're primarily concerned with delta S of the system that we're measuring, not the delta S of the universe as a whole, right? So the easiest way to look at delta S is to compare your starting materials to your products. Oop. Positive or negative. Let's say we have more moles of your products. So we're creating 3 moles and we maybe started with 2. Is that more disorder or less disorder? More. We went from a 2-mole mixture to a 3-mole mixture. We're creating more disorder. So should this be positive or negative? Positive. So we'll say delta S for the system is positives. Okay. If we have fewer moles of products than reactants, the inverse of that is true, and we can say delta S for our system is negative. But there's also one other feature we've got to look for as well. Increase in freedom of motion. Or we can look at a decrease in freedom of motion. All right, if we're increasing our freedom of motion, meaning we can rotate in more directions, are we increasing disorder? Yes. And so what would delta S be? Yeah, delta S system is going to be positive, and the inverse is true. Delta S of our system would be negative if we're decreasing freedom. So I'm going to give you guys some examples, and I want you to predict whether or not delta S is positive or negative. Oops, sorry. All right, first example. One of my favorite reactions that we'll cover, I think in second term, called the Diels-Alder reaction. We take a diene, meaning an alkane with 2 alkenes on it, and a normal alkene. We react these together, and when we do, we form a new ring. Right? All right. Have we created more disorder or less disorder? Less disorder, right? Because we started out with 2 moles of starting materials, 1 mole of each, and then we're getting 1 mole of product. So less disorder. Therefore, delta S for our system, is that positive or negative now? Yeah, negative. So we don't know the degree to which it's negative, but we know that the sign is going to be negative. All right, let's do another example. The next example I have is a 5-membered ring with oxygen in there. There's a methyl group coming off of the oxygen and 2 methyl groups coming off of one of the carbons. All right, and what we're going to do is essentially we're going to break this sigma bond and move those electrons up to oxygen. Okay? How many moles did we start with? 1. So we've got 1 mole, 1 mole. So have we increased entropy, decreased entropy, or is it staying the same? Which one can flop around more? Second one. So more floppy equals increase in molecular freedom. So, is this an increase in entropy or a decrease in entropy? Increase. We went from being constricted, it couldn't flop around as much, to being linear, where it can rotate freely through space, as we saw with our Newman projections and rotations. Yep?
You did my question, like, the systematic way to figure out whether or not the molecules are floppy as opposed to the other one.
Yeah, if you're confined in a ring system, you typically can't rotate as much, right? But if you're linear, you can draw Newman projections for all of those carbon-carbon bonds rotating freely through space. So I call it a floppy molecule. It's not tied up. So S of the system is positive. All right, there's one really important feature with entropy, though. What does disorder depend on? Heat or temperature, right? So if I apply heat to something, it becomes more disordered, right? You can think of that even in terms of applying heat to the point where you combust it. You're disordering that molecule to a fairly extensive degree. So entropy is closely related to temperature. All right, how do we tie enthalpy and entropy together? Anybody remember? There's another energy term out there. Not delta H, not delta S. Delta G. Does anybody remember what delta G stands for? Gibbs free energy. Good, good. This is great. Gibbs free energy. Gibbs free energy looks at a reaction spontaneity. Temperature. So Gibbs free energy looks at a reaction's spontaneity. I'm not sure if I'm spelling spontaneity right, but I'm going with that one now.
That's right.
Is that right?
Yeah.
Okay. All right, we're looking at a reaction spontaneity. Does anybody remember the equation for Gibbs free energy? Delta G equals delta H minus T delta S.
I knew that all along.
You guys all knew that, I'm sure. So we've got Gibbs free energy over here. We've got the enthalpy for the reaction. Oop. Over here we've got our change in entropy. And then last but not least, we've got the temperature. All right, we're going to use Gibbs free energy a lot in this class, but in order to look at Gibbs free energy, I oftentimes draw it out using an XY graph. And so I wanted to introduce you guys to reaction coordinate diagrams. All right. So on one axis, we have delta G. Okay, so that's our measure of free energy in the system. In the other direction, we've got reaction progress. Let's say we've got our starting materials over here, and we've got our products down here. Is this reaction going to be spontaneous? What do you guys think?
Yes. Yes.
Does it require energy to roll downhill? No, it's spontaneous when you roll downhill, right? So we've got a downward path from starting material to products. So in this case, our delta G value, oops, sorry, that should just be G. Our delta G value
What is the S
starting material.
Can you just call it reactants?
Yeah, you can label it as starting materials or reactants, however you want to name it. But we're rolling downhill. Delta G is negative, Is this reaction going to be spontaneous? Yes. Reaction is spontaneous. And what we call this when a reaction is spontaneous is it's exergonic. Oh. There we go. There we go. So the reaction's spontaneous, it's exergonic, we're rolling downhill. Is this the true story of what's going on in this reaction, though?
No.
Not quite. We have something called an activation barrier, or activation energy, that's required for a reaction to occur. Otherwise, spontaneous reactions would occur without warning. If you're transporting a truckload of TNT, that's bad news, right? You don't want that to occur spontaneously. You want to be able to push the reaction over a hill and then have it occur spontaneously. So, the other side of this is with this hill that we have to overcome. And this is called EA, which is our activation energy. We're going to talk more about this, but I just wanted to show you guys the difference between the Gibbs free energy change versus the activation energy. Some of them have really, really high activation energies that essentially make the reaction improbable, meaning it won't happen unless you apply an incredible amount of energy to get it over that initial hill.
So this is equal?
Not necessarily. You can have humps of different sizes. Let's compare this to a separate chart. Closely related. We still have G on this axis, and we still have reaction progress over here. But this time we've got our starting materials at a lower energy, and we've got our products up here. What do you notice about our delta G? Positive now. We're pushing the boulder uphill. Takes a lot of energy. And same thing as before, we also have a hump we have to overcome. That's right there. And in this case, what's our delta E going to be? Or sorry, our EA. All the way to the top. EA is a measure of how far you have to climb over that initial hump of the hill in order for the reaction to proceed. So we've got EA over here. Let me fix this and make it drop down a little bit more. There we go. And so in this one, delta G is positive. Does that mean this reaction is spontaneous or non-spontaneous? Yeah. So the reaction is non-spontaneous. Meaning it's probably not going to occur under most circumstances. What we call this is endergonic. So we're going to use a lot of these reaction coordinate diagrams when we look at a reaction. And not only are we going to look at the hill we have to climb to get over, but how far downhill is the ultimate product going to be? Is it going to be really, really far downhill? Or is it going to be a small change? What change is that delta G value going to be? All right, let's look at an odd example, though. All right, we run a reaction, and delta H is negative. Actually, where delta H is negative. And delta S is also negative. So let's first describe what this means. If delta H is negative, does that mean the system's releasing heat or absorbing heat? Okay, so we know it's releasing heat. So it's exothermic. And if the delta S is negative, what does that mean? Are we becoming more ordered or more disordered? More ordered. So it's releasing heat and becoming more ordered. So let's think about this. We can plug this into delta G equals delta H minus T delta S.
You move on.
Yeah. And if we think about our delta H value, the sign for this should be what? Negative. And then over here we've got a negative. So is delta G going to be negative or positive? Depends on the temperature, right? So let's rewrite this a little bit so some people can see it. Another way of writing Gibbs free energy is to do delta G equals delta H plus negative T delta S. So we can go through and we can say, all right, if this is negative and this is negative, the sign depends on T. Right? So when will delta G be negative? If T is really, really hot, large or hot, right? So if T is a very, very big value, let's think about that. Or sorry, I'm flip-flopping it in my head. If T is a really big value, what does that do to delta G? It makes it more negative. Or sorry, oh my goodness. This is making my head spin now a little bit. Yeah. All right, if T is large, then delta G is positive. Right? Because the negative for the delta S cancels out with the negative that's already in the delta T, which is going to increase that delta G value. And if T is small, then delta G is negative. Right? So if T is large, that T delta S side of the equation predominates. If T is small, then that T delta S side of the equation is pretty insignificant, and delta H predominates. So we can control the reaction. If we want this reaction to be spontaneous, should we be running it at a high temperature or a low temperature?
Low.
Yeah, if we want the reaction to be spontaneous, we want delta G to be negative, and the temperature should be low, right?
So is that the general rule or just for this equation?
Just for this equation. It always depends on your sign of delta H and delta S. So if we want the reaction, whoop, shoot. Sorry, guys. If we want the reaction to be spontaneous, then we should run it cold. Or run it at a low temp. That's the only way to get delta G to be a negative value and have this reaction be spontaneous. Which makes sense. If we go up and we look at it, we said delta S was negative, which means it's going to be more disordered, more ordered, right? So if we're trying to make things more ordered, do we want to apply a lot of heat to it? No. In fact, we want it to be as cold as possible. Heat drives disorder, so denying it of heat will help you in that process of making things more ordered. So it's a kind of odd and unique example, but it shows why we don't just look at delta H. We also have to factor in delta S for the reaction. Does that make sense? Yeah, it gets tricky. All right, let's talk a little bit about how this relates to equilibria, or reactions that are in equilibrium. So let's think about this reaction coordinate diagram where we've got G over here, and we've got our reaction progress over here. And we've got this equilibrium where it's A plus B is going to C plus D. So up here I've got A plus D, and then I've got C plus D. Oh, sorry, A plus B, not D. Is this reaction at equilibrium? Let's think about it. If it's at equilibrium, do you think it would spontaneous flow, where we'd have spontaneous reactions going towards C and D?
Well, yeah, but assuming it goes back.
Yeah, assuming it goes back. But let's compare a second example. Let's say I've got G here, and I've got my reaction progress here. And I've got A plus B, and then C plus D. And they're at the exact same energy level. Is that at equilibrium? Yeah, at equilibrium, you're not flooding one side of the reaction with products, right? It's a balance between starting materials and products. So this would be a non-equilibrium reaction. This one over here might have a hump. And somebody was saying, well, the pathway that for A to B to go to C to D should be the same as the pathway going from C to D backwards, right? So this would be true equilibrium conditions. So at equilibrium, whoops. Delta G equals 0. If delta G doesn't equal 0, then the reaction isn't at equilibrium. Oh, shoot, why is it doing that? All my words went away. Here we go. So if it's not at equilibrium, does that mean it's permanently stuck at non-equilibrium conditions? No, what will eventually happen? It'll even out, right? So we can look at an equilibrium and we can say this is pre-equilibrium. Things aren't quite balanced yet, but if we let it sit there long enough, things will bounce out and delta G will eventually approach 0. So we can also draw this using, am I going too fast? No. Your hand's going to fall off. I apologize. All right, let's draw this. So we've got G over here for Gibbs free energy. And let's say on this side we've got only A and B in solution. And then over on this side we've got only C plus D in solution. I'll abbreviate solution there. All right, if we've got only A and B in solution, is this at equilibrium? No. Is delta G going to be high, or is it going to be 0? It's going to be quite large, right? So on this axis, we've got 0 down here. So I'll even write in 0. At this point, it's going to be some arbitrarily high level of A. And then what if we only have C and D in solution? Meaning no A and B. It's also going to be high. It's not at equilibrium. So we can draw this up here and we can say, all right, that's also high. Now we need to connect this with a line or a curve. What do you think will happen? It'll dip down, right? So eventually we'll kind of reach down like that. What's happening at this point?
We have equal.
Yeah, exactly. This is equilibrium.
We will reach the bottom line or not?
Yep, it should be at 0.
Oh, okay.
Yeah. Delta G equals 0. So delta G drops as we get closer and closer to equilibrium, meaning when it's only at A and B, the reaction is very, very spontaneous. It rapidly wants to go towards equilibrium, but as you get closer and closer, the reaction's like, we're almost there. I'm not going to be as urgent as I am if I'm way up at the top of the crest. Once we hit equilibrium, we can also overshoot the equilibrium a little bit and then correct ourselves back into this well. So the way I like to think of it is if you drop a marble at the top where you have only A and B, the marble is going to roll down, go up, 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 and then eventually settle at this point where we're at equilibrium conditions. So at that point, it's non-spontaneous. The reaction won't proceed, at least non-spontaneous, or it won't proceed spontaneously towards the A and B side or the C or D side. All right, I think I'm going to end class just a couple minutes early because I don't want to fry your guys' brains with the next concept. But make sure that you guys do start on the problem of the day tonight. It does require you going through that table 6.1 and thinking about Gibbs free energy a little bit more critically.